some sort of variations of things you might want to try are things like people say, I know how to beat the breathalyzer. And one thing that I had heard before is people say, well, I'll do a mouthwash just before I do the breathalyzer test. Well, two things there. One, if they use something like scope, it's 15%. You can actually put this in your balloon and you'll get a positive test. And just put a couple of, just a small amount and do the same thing with the alcohol and you'll get a positive test. Another thing.
Can I
sure.
ask everybody a question? This brings up something really good you can do with your students, is if they've probably heard this somewhere about the mouthwash and alcohol containing mouthwash. And what Myra just told you was the chemistry part to that story. But I think it might be useful for you to get the kids to think about the biology part of that story. And so, although in the chemistry test tube experiment you can get a positive test on the breathalyzer with the scope mouthwash, is it likely that someone would get a positive test if they were to be stopped by law enforcement and taking a breathalyzer test? What do you guys think?
Wouldn't the alcohol evaporate too fast?
Yeah, that's what I was going to
Depends on when they were.
Do you know how the breathalyzer test is given?
It's really, oh, okay, no, I wasn't gonna answer that question.
Well, what were you
If
going
you know about that, I'm worried.
Well,
I don't wanna show too much knowledge here.
Okay, all right. Well, let's say secondhand knowledge. Okay,
Oh, okay.
all right. If you have secondhand knowledge,
from Texas.
A friend.
Secondhand knowledge is I had access to a breathalyzer, and a mouthwash containing alcohol will continue to register on that for about 15 to 20 minutes.
okay,
Depends when they get stopped.
How does the test?
That was me.
okay.
That must be you.
My secondhand information is, and you know that the law enforcement people that are actually administering this have been trained and they know all of the things that they've heard on the web about what will beat the test. And so the law enforcement agents they sort of have a protocol that they go through before they ask you to blow into the breathalyzer. And so they're not going to let you run upstairs and do all the things that you read about on the internet. And what they do is they ask you to inhale and exhale, and there's a certain amount of time they wait, and then inhale and exhale. And then there's a certain point in that exhalation that they actually collect the breath. And in the breathalyzer, they only take like 50, I think it's 51 or something, they vary, but the one that I read about takes only 51 milliliters of air. And so that 51 milliliters of air that you're breathing out is actually what they're measuring. So they're very careful about that. Last night's broadcast, one of the teachers said that one of her students said that they could beat a breathalyzer by putting a penny under their tongue. And so when we had a break, I went over into my office and got a penny, and I put it in the neck of the balloon. See right here, I've got a dark balloon. I put the penny in the neck of the balloon. I put a drop of alcohol and blew it up and did the whole thing all over again. And I got, let's see, where is it? Here's the test I got from the penny. So that myth didn't keep that guy from getting a ticket. So it's kind of fun when the students come in with different ideas of how you can actually debunk their myths. Are there things that you guys have heard about how to beat a breathalyzer test?
Nothing as a penny in the mouth.
Pardon?
Nothing as creative as a penny in the mouth.
Yeah.
Now, is the penny in the mouth thing for the chemist dependent on something about copper interacting with this particular equation. Can we put the equation on the,
Yeah, yeah, there it is. Okay.
what would copper do to that?
Yeah, copper's not reactive.
It would provide a surface, but that's about all it would do. I can't imagine any chemical reaction. Okay. I teach AP chemistry, and since I wanted to take this qualitative example and make it quantitative. And so what I did was using, I've just done, this time of the year, I've just finished sort of the review of all of first year chemistry with all the stoichiometry. And so I was looking for a good example where they would really have to apply their knowledge of stoichiometry. At the same time, I could meet another AP chemistry objective, and that was doing a Beer's law plot. So what I did was I made standard solutions. You can see nice, pretty standard solutions. And I made one of the concentrations, like concentration, the second or third concentration, and I put 1 milliliter of an unknown concentration of alcohol, and we put that in a water bath, and we added silver nitrate as a catalyst, and we let that stay in the water for about 45 minutes. And then we tested that to our Beer's law plot, so that they had to figure out what the blood alcohol level. So we sort of simulated using Beer's law to do an a quantitative lab. And that lab is written up and is also on the Moodle. So there's probably some questions about that, because I've only done it once with the students, and I haven't had a chance to go back and make a whole lot of edits. But at the end of that, you will find all the materials and how to make the solutions. In the beginning of that activity, there's also a pre-lab. So if you wanted to give your students some pre-lab questions to get them to sort of think about the stoichiometry, and also do something that Suzanne's going to talk about in a minute, about the blood alcohol, how to do the mathematical calculations. One other thing that came up in looking at if we go back to the equation, it's real obvious, and I think some of you mentioned already, what gets reduced. You want to tell me again what got reduced?
Chromium.
All right, in the dichromate, the chromium went from a +6 to a +3. What got oxidized?
Ethanol.
All right, and if you look at, those of you that teach the AP chemistry, and you look at the ethanol molecule going to acetic acid, and you try to do a half reaction on that, one of the teachers Monday night was a little concerned, because when she tried to apply the half reaction, she got a 0 for for carbon, and she was a little bothered by that. Does that bother anybody here?
What's going on?
You can have different charges.
Yeah. So what I try to explain to my student is when we're doing oxidation reduction, we're really doing an accounting system. We're actually trying to track electrons and where they go, and we're not talking about a physical charge on the carbon. We're talking about the keeping track of where the electrons are. And then that makes it, if they understand that, then when we get to the point of Lewis acids and bases and sharing electron pairs or donating electron pairs, it makes it easy for them. All right. Any questions about the lab activities or the chemistry of the breathalyzer? All right, Suzanne?
I just wanted to compliment you. This is very doable and it works, so good for you.
All right, thanks.
Okay, so just to review, I wanted to start off again by showing you another nice animation of this breathalyzer test. And while it's going on, we could talk a little bit about inside the breathalyzer chamber. And every test, every good experiment, right, has a control. And so that's not left out from this breathalyzer test as it's administered even on site. And that's because the color change that happens in the chamber that's exposed to alcohol actually is compared with a photocell to a control chamber that's completely closed off and doesn't receive any ethanol. And this way, the device is actually able to come up with a calculation based on a standard. And there you go. That's just a picture. And Myra sent us a nice link not too long ago. It seems that now you can have your own breathalyzer on your person with an accessory for your iPod. So, despite the fact that these types of breathalyzers are sort of being outdated, even right now, as we're going through the technology, the new types of breathalyzers are becoming more and more sophisticated and are supposed to be reportedly have better accuracy. And we'll be touching on that in a minute. And the schematic below is actually animated, and so once the person exhales, you can see that the orange potassium dichromate then changes to green, very, very much like the interactive Dranius noise. That'd be great. Okay, so are there any questions again about the device or the actual reaction? I did want to mention one thing that I left out, and that is that, let's see if I can go backwards with this thing. In this equation, I kind of skipped right over. It's my understanding that the sulfuric acid in the reactants for this equation serves to help condensate or precipitate the ethanol that's coming in as a vapor back to its liquid form. And that's the purpose of this. In fact, silver nitrate is the catalyst of this reaction. Okay, so just moving forward and covering the very end of this student handout. So we've talked about circulation, we've talked about volatility, equilibrium, a little about oxidation and reduction reactions. So now, how is it that the breathalyzer test is able to approximate the blood alcohol concentration? How does that happen? So we've talked a bit about the device, and so now let's talk about how that approximation happens. It turns out that the degree of color change indicates how much alcohol is present in the expired air. And the instrument then calculates the actual concentration, as I mentioned, by comparing it to another chamber, a test chamber that's never exposed to alcohol. However, in order for the breathalyzer to make this calculation and determine how much alcohol is actually present in the expired air sample, it has to take into account the volume of the blood from which it was actually sampled. And there's a standard way of describing this relationship in the literature known as a partition ratio or a partition coefficient. And all that is to say that the average blood to breath ratio is 20/100 to 1. And this is the value that they use for legal purposes in making the determination for the breathalyzer test. So this ratio...
I'd like to make a suggestion.
Yes.
Those of us who are novices in working with this ratio, it is called a blood to breath ratio, but the way it was presented as 2100 to 1 is actually a breath to blood ratio. So it was really confusing. I know those that have worked with it before, it's by convention, so you get it, but it took me a while to figure that out.
Okay.
Was there a typo? Is that what happened?
It's the order.
No.
The order of the word was switched.
We'll fix that.
So,
Okay, thanks, that would help.
So this ratio actually assumes that an equilibrium exists between the blood and the alveolar air. And so we already talked about how that would happen when the concentrations equilibrate across the alveolar membrane. Now, did some of you come across a definition for this ratio? It's more complicated than some of the others in terms of just finding it by searching. So what I did was I actually made a schematic that I thought kind of best described, and it's inadequate at best, but I I never got up to 2100 molecules, but the way I was thinking about it was that compared to the blood, if you took a 1 ml sample, you would have 2100 times the number of ethanol molecules in the blood that would be present in the breath at any given time. And as I said, it wouldn't be obvious from looking at this because I never got up that high in the number of molecules here. But if you just compare the two chambers and you consider a similar volume, you would have much fewer molecules moving around in that same volume of breath than you would in the blood. Now, why do we have this sort of ratio? And that allows us to test something coming from the breath and then back calculate to determine what the actual blood alcohol concentration would be. Now, I think importantly, we hear these numbers and we think, well, that's what they use to make calculations that are for legal purposes, but that doesn't always mean it's absolute or even correct or accurate to use this. So we discussed last week, actually, that we differ a lot amongst ourselves in our metabolism rate of alcohol. So, for example, someone who has a very high metabolic capacity for ethanol, for example, because they have an enzyme in their liver that works very efficiently, on a bell curve of the entire human population and how they fall out in terms of ethanol, their blood to breath partition ratio, it would be quite different if you just considered two individuals with very different ability to metabolize ethanol. Does that make sense? So if a lot of the ethanol is taken out in that first pass through the liver, the amount that actually enters the bloodstream and then would be carried to the lungs is going to be less. So it seems obvious that we would generate a bell-shaped curve for all the people that would be tested for their accuracy using a breathalyzer and back calculating for the blood concentration. Turns out that this factor, this ratio, can range anything from 1,500 to 1 up to 3,000 to 1. And so we've just asked if using those ratios at the outer limits, if based on a 0.08% breathalyzer or blood alcohol concentration as estimated from a breathalyzer, what would be the range of values that you would get at either end? Does anyone want to tackle that that question?
Well, I can tell you what I got, but
Great.
At the if you're using, let's see, the 1,500, you actually end up with a 0.05% BAC, and if you are at the 3,000 level, it's like 0.11%.
Yeah.
Right, so this is hypothetical because I imagine at 0.11 you would be
Did you work it out just with the ratio?
more than just intoxicated. So I put the steps that I took up here just so that you can see kind of how I went through this. But this is just working with ratios, first understanding how the concentration, the ratio of the concentrations become in equilibrium, and then second, actually going through a mathematical calculation to estimate the overestimation or underestimation. And again, I derived the same values that Gail did by taking the factor of difference that you would have 2,100 to 1,500 as a factor of 1.4 difference and going back and multiplying that by the original BAC as calculated from the breathalyzer test and coming up with the 0.11% and likewise the 0.06%. So again,
You got yours in a much easier way.
okay, so tell us what you did, Gail.
Well, I was having a lot of trouble understanding exactly what this ratio was and how it was supposed to be used. That may
Okay.
just be my lack of understanding, but it just was not intuitive. I guess that's a good way to put it. And so I actually went back and used the ratio, etc., and her beginning 0.08%, and went back and figured the actual particle count.
Oh, okay.
for alcohol in each one of those. So I'm talking 10 to the -7th kind of stuff.
Well, that's great, and obviously it worked, and it came out with the same answer. So, and the principle, I think, would just be that they see that that first, that the this is a test, and of course a blood test is much more accurate. It is, the blood test will give you the blood alcohol concentration, whereas a breathalyzer test is estimating the blood alcohol concentration. And those estimates, of course, that we see in the literature, that a lot of science is based on, are actually reflective of a science experiment that went on before that, where many people in the population were tested with a breathalyzer test to approximate their blood alcohol. And then at the same time, a blood alcohol test was taken, and they tried to compare to see how accurate that was. And this calls into question, because a person with a 0.06 would legally not be intoxicated most places, whereas a person with a 0.11 would be probably more than seriously intoxicated.
Hey, if I could put something in also, I don't know if mine's just aesthetically more pleasing or what, but I just set up a simple ratio that most of my kids could have done, where I put 0.8 over 2100 is equal to X over 3000.
Great, yeah.
It's
So
exactly
basic.
the same what you did, but probably my kids would handle my math easier than what you had done.
I agree. If any students that have had algebra certainly would, that for them that would be very straightforward. As it turns out, we actually have some ninth grade students that we teach during the summers, and we find that some of our ninth grade students are coming in a little behind the curve and haven't actually had their algebra yet, and so they have a difficult time with that unknown X yet. But I agree. It's for students who've had algebra, that certainly would be another way to go about calculations, and one that they would be very familiar with.
And also, I'll throw in something here too. My own personal learning style is to not use equations, and when I have students come into my lab and have to do calculations or figure out concentrations and things, I actually have them do it without using equations. Just use logic and do it in words without having to actually use. It's very funny, they all want to use equations. They memorize the equations and they sit there trying to use the equations and plug things in. And a lot of times I take the paper away and I say, just forget the equations, just think about it logically. And what would you do? And usually after they've done that a few times, they really like it.
So certainly you can gauge based on your students' math abilities, and I guess this speaks to the idea that we're finding that that there are lots of ways to integrate math into your science curriculum, and you'll find the ones that are best and most comfortable for you in the classroom. But as a suggestion, this is one way that you could get students to start thinking about the accuracy of these tests, or how they might evaluate it, and where the data actually comes from that establishes these partition ratios in the first place. And what would happen actually if you fell under a person who is on the outside end of the bell curve on either shape? What it basically means for them, even in terms of legal purposes. So if there are not any additional questions about the breathalyzer, I think what we'll do is, I did want to make one more comment, which is thank you everyone for participating. And I had also sort of outlined here that we had expectations for the students that we wrote as learning objectives, but certainly as you gauge your classroom, those of you teaching more advanced students, there are lots of things you could do with this, including instead of just having them understand the path of circulation, you could go one step further. You could give them a different route of administration. Vaporized alcohol into the lungs, about the devices that we were talking about last week. And you could ask them to then predict their route of circulation given a different route of administration. And these are things that learning skills that an advanced student or a student having already completed the curriculum might be able to do. And again, that things like balancing the redox equations, like Myra was showing you. Of course, these are applications that would be great for a